Welcome to this lesson on organic analysis. In this topic, you'll learn how chemists identify unknown organic compounds using simple chemical tests and spectroscopy. By the end, you'll understand functional group tests, chromatography, mass spectrometry, infrared spectroscopy, and proton NMR spectroscopy. Purpose and scope of organic analysis in A-level chemistry, overview of required analytical techniques in the A-level specification, link between organic analysis and required practicals, exam expectations, and command words in organic analysis questions. Organic analysis determines the functional groups, structure, and purity of organic substances using a combination of chemical tests and instrumental techniques. Organic analysis is functional group identification. Therefore, organic analysis also focuses on instrumental methods, which provide more precise and reliable data about molecular structure. Analytical techniques are grouped into qualitative chemical tests, chromatography, and spectroscopy, each providing different types of information about organic compounds. Qualitative chemical tests include tests for unsaturation using bromine water, identification of aldehydes using Tollens reagent, and the use of Feeling solution to distinguish aldehydes from ketones. Chromatography, including thin layer chromatography, TLC, paper chromatography, and gas chromatography, GC, is another required area. Spectroscopic techniques form the most data-rich part of organic analysis. Infrared spectroscopy is used to identify functional groups, while mass spectrometry provides molecular mass and fragmentation information. Practical activities such as chromatography experiments, preparation of organic compounds, and testing for functional groups provide students with real data that mirrors exam-style questions. One key practical skill is the use of chromatography to assess purity and identity. Functional group testing is another major practical area. Performing tests such as the bromine water test or 2,4-DNPH reaction allow students to observe color changes and precipitate formation firsthand. Finally, while students may not operate advanced instruments like NMR spectrometers in school laboratories, practical work introduces the idea of data collection and interpretation. Common command words include identify, deduce, suggest, and explain. For example, when asked to identify a functional group from an infrared spectrum, students must link specific absorption peaks to bond vibrations. In contrast, a question that asks students to deduce a structure requires the integration of multiple pieces of evidence, such as molecular mass from mass spectrometry and splitting patterns from NMR spectroscopy. Qualitative tests for functional group identification, principles of chromatography and separation techniques, RF values, and their use in identifying compounds, applications of gas chromatography in organic analysis. Qualitative chemical tests are a fundamental part of organic analysis and provide rapid evidence for the presence or absence of specific functional groups. One of the most important tests is the bromine water test for unsaturation. Alkenes react with bromine water, causing the orange solution to decolorize as bromine adds across the C=C double bond. Another key test is the use of 2,4-dinitrophenyl, 2,4-DNPH, to identify carbonyl compounds. The formation of an orange or yellow precipitate indicates the presence of an aldehyde or ketone. Chromatography is a versatile analytical technique used to separate components of a mixture based on their relative affinities for a stationary phase and a mobile phase. In organic analysis, chromatography provides valuable information about the number of components present and can aid in identification when compared with reference data. RF values are a quantitative way of describing the movement of substances in paper or thin-layer chromatography and are central to identification in organic analysis. The RF value is defined as the distance traveled by the substance divided by the distance traveled by the solvent front. This ratio has no units and lies between 0 and 1. Gas chromatography, GC, is a powerful analytical technique used to separate and analyze volatile organic compounds. In GC, a small sample is vaporized and carried through a long column by an inert gas such as helium. The column contains a stationary phase that interacts differently with each component. Compounds with lower boiling points or weaker interactions travel faster and reach the detector sooner, producing peaks at shorter retention times. Principles of infrared spectroscopy, interpreting infrared spectra for functional groups, mass spectrometry, and molecular ion analysis, using mass spectra to deduce structure. Infrared (IR) spectroscopy is a key analytical technique used to identify functional groups in organic compounds by analyzing how molecules absorb infrared radiation. Different bonds absorb IR radiation at characteristic wave numbers, measured in cm to the power of 1. For example, OH bonds produce a broad absorption around 3200 to 3600 cm to the power of 1, while C=O bonds show a strong, sharp absorption near 1700 cm to the power of 1. By recognizing these patterns, students can identify functional groups present in a compound. Interpreting infrared spectra is a skill that requires careful observation and systematic analysis. One common task is distinguishing between alcohols, carboxylic acids, and carbonyl compounds. Alcohols show a broad OH absorption, whereas carboxylic acids show an even broader OH peak combined with a strong C=O absorption. Aldehydes and ketones both show C=O peaks, but aldehydes may also display a weak CH absorption around 2700 to 2900 cm to the power of 1. Mass spectrometry is a vital technique in organic analysis, providing information about the relative molecular mass and structure of organic compounds. When a compound is ionized, usually by electron impact, it forms a positively charged molecular ion. This ion may then fragment into smaller ions, producing a pattern of peaks. The molecular ion peak has the highest MZ value and allows students to determine the relative molecular mass of the compound. Beyond identifying molecular mass spectrometry can be used to deduce structural features of organic compounds through careful analysis of fragmentation patterns. For example, a prominent peak at MZ43 is often associated with the CH3CO+ ion, suggesting the presence of an acyl group. Similarly, peaks resulting from the loss of small neutral molecules, such as H2O or CO2, can indicate functional groups like alcohols or carboxylic acids. Fundamental principles of proton NMR spectroscopy, interpreting chemical shift, integration, and splitting, combining analytical techniques in synoptic questions, summary, common pitfalls, and exam preparation strategies. Proton nuclear magnetic resonance, to the power of 1 HNMR, spectroscopy is one of the most detailed analytical techniques in organic analysis and provides information about the number and chemical environment of hydrogen atoms within a molecule. In to the power of 1 HNMR, hydrogen nuclei are placed in a strong magnetic field and absorb radio frequency radiation at frequencies that depend on their chemical environment. This absorption is recorded as peaks on an NMR spectrum, with chemical shift values measured in parts per million, ppm. Different functional groups and bonding environments produce characteristic chemical shifts. Interpreting to the power of 1 HNMR spectra requires students to consider chemical shift, integration, and splitting simultaneously. Chemical shift values indicate the electronic environment of protons. For example, protons attached to electronegative atoms or near pi systems appear at higher ppm values. Integration provides the relative number of protons in each environment, which can be matched to parts of a proposed structure. Splitting patterns arise due to spin-spin coupling between neighboring protons. The n+1 rule states that a proton with n neighboring protons will be split into n+1 peaks. For instance, a triplet indicates 2 neighboring protons. Typically, students may be given results from functional group tests, chromatography, IR spectroscopy, mass spectrometry, and NMR spectroscopy. Each technique provides a piece of the puzzle. For example, IR spectroscopy may identify a carbonyl group, mass spectrometry may give the molecular mass, and NMR spectroscopy may reveal how carbon and hydrogen atoms are arranged. A strong summary understanding of each analytical technique and how they work together is essential. To summarize, organic analysis combines chemical tests with chromatography and spectroscopy. Learn the characteristic reactions, recognize key spectral features, and practice interpreting data. With regular practice, you'll become confident at identifying unknown organic compounds in your exams. Thank you for watching.